Today, we are going to understand the theory of plate tectonics. We will learn why continents have been slowly moving over millions of years. We will understand why areas like Western America or Southeast Asia experience a huge quantity of earthquakes. And we will also discover why volcanoes appear where they do. So if you want to understand all of this, watch the full video. Let's embark on a fascinating geological journey to better understand how the Earth's crust works. So, get ready, activate your neurons, and tighten your seatbelt, because our scientific journey is about to begin. In the 1950s, our understanding of the geosphere had advanced significantly. In just about 50 years, it had been discovered that the Earth was not a solid sphere, but was composed of different layers. The exterior was solid and rigid, and the interior was molten and had extremely high temperatures. It had also been theorized that continents had moved from one place to another. However, nobody could propose a final theory that could neatly connect both ideas. A theory that could explain the continental drift that Alfred Wegener had failed to explain. Why did the continents move? And what was the relationship between this movement and the layers of the Earth? In 1919, Arthur Holmes proposed one of the earliest models to explain plate movements, a theory that was later adapted into modern plate tectonics. His hypothesis suggested that a large convection currents in the mantle drove the movements of the plates. Let me take a step back here. You might be wondering, what exactly is a convection current? Well, basically, they're kind of like squirts of super hot magma that come from the deeper mantle up towards the crust. But, obviously, you cannot write a scientific article referring to something as a super hot magma squirt. So, Holmes decided to name it convection current. These convection currents explained the ascension of hot and less dense rock, which, when it comes into contact with the lithosphere, would drag it along, kind of like a conveyor belt. Once the material cooled down as it moved away from the core, it would sink back down into the lower mantle where it would be reheated, thus dragging parts of the lithosphere downwards with it. Holmes postulated that where these super hot magma squirts, where two convection currents coincided, an area of compression would appear. Here, at these areas, the crust would be pushed back into the Earth's interior. To counterbalance this disappearance of crust, new oceanic floor would be formed where the currents ascended. Certainly, this theory sounded good and even made sense. And, although it had some errors, it was surprisingly close to reality. But, Holmes had no evidence to support his theory. Except, something really similar to his proposal happens when we, say, boil water in a pot. These same convection currents form. But of course, that doesn't count as definitive evidence. Just because it happens in a pot in your kitchen doesn't mean it's happening deep inside the Earth. Further research was necessary. Then came along World War II, the brutal global conflict that devastated the world between 1939 and 1945. But it also brought significant technological advancements. Sonar technology, which was used to detect enemy submarines, improved exponentially during this period. Sonar essentially operates by emitting sound signals underwater, which, upon bouncing back up, allow for the identification of submerged objects. This improved technology could also be used to send signals towards the seabed itself, letting us know its depth and help with the creation of a detailed map of the ocean floor. During the 1950s and 60s, oceanographic vessels were used to do an extensive mapping of the seafloor. In 1957, Bruce Heesen and Mary Tharp published the first detailed map of the North Atlantic seabed. This study of the ocean floor revealed something quite surprising: a global system of oceanic ridges, which are large volcanic mountain chains extending for thousands of kilometers. It was also observed that the Mid-Atlantic Ridge ran parallel to the continental margins on both sides of the Atlantic. Additionally, it was found that the system of oceanic ridges was characterized by intense volcanic activity. In other parts of the ocean, even more discoveries were made. Large depressions in the seabed, known as ocean trenches, were discovered. Studies on earthquakes identified significant seismic activity at great depths under these trenches. Furthermore, when rocks were extracted from the seafloor, none were found to be older than 160 million years old. In contrast, numerous samples from continental crusts have been dated to be much, much older, up to 4 billion years old, in antiquity nearly reaching the Earth's estimated age. So from that, several mysteries emerged. Why are rocks in the continental crust so old, while those in the oceanic crust are relatively young? And why do earthquakes occur at great depths beneath the already deep ocean trenches? In the 1960s, Harry Hess tied together these new findings about the seafloor in a hypothesis called seafloor spreading. Unlike Wegener's theory of continental drift, which, due to his lack of knowledge, disregarded these ocean basins, Hess's theory focused on this submarine activity specifically. He built upon Holmes's ideas and proposed that oceanic ridges were located in areas where molten materials from the Earth's mantle ascended to the lithosphere. As the ascending materials encountered the rigid and solid crust, it was forced to move laterally, or to the side, scraping and pushing the seafloor as if it were a conveyor belt. By pulling the seafloor in two opposite directions, tensile forces would fracture the crust, creating space for new magma to seep in and form new, young oceanic crust. Therefore, the seafloor would be constantly replaced by newly formed crust. And do you know what else Hess discovered? That it was essential to give the video a like and subscribe to the channel. I swear, I was reading his super famous book, Subscribe and Like to Awesome Geohistory Videos, and he mentioned it on the first page. Obviously, I'm kidding, but if you are enjoying the video, please don't forget to hit the like button and subscribe. Something as simple as clicking like, subscribing, and also hitting the notification bell is crucial for keeping the channel going. So if you do that, thank you so much. Anyway, let's get back to Hess. He also suggested that deep ocean trenches, such as the Peru-Chile Trench, are places where the oceanic crust returns to the interior of the planet. However, while Holmes believed that both plates were compressed and both descended into Earth's interior, he pointed out that in these trenches, only the oceanic crust descended back into the Earth's mantle, leaving continental crust on the surface. Since the mantle is at very high temperature, the oceanic crust eventually melts into magma. In other words, Hess's theory explained that the oceanic crust is young because it's constantly being renewed, and while the continental crust remains afloat on the surface, forever aging. Hess's theory was almost complete, but there were still things that needed to be explained. For example, geological studies of the seafloor had also revealed geomagnetic reversals. It meant that it had been discovered that on both sides of oceanic rifts, there were bands of rocks with either normal or reversed magnetic crystallization. Fred Vine and D.H. Matthews were the scientists who managed to provide a coherent explanation for the appearance and pattern of these magnetic bands in the seafloor, and how it related to their creation and movement. During the same time that Harry Hess formulated his hypothesis of seafloor spreading, geophysicists discovered that the Earth's magnetic field experiences periodic changes in polarity. This means that the magnetic North Pole moves to the geographic South Pole and vice versa. So even though the magnetic North Pole is currently located in the north, it doesn't mean it has always been there. In fact, we shouldn't think that the geographic North Pole, which is the imaginary point where all meridians meet at the top of the Earth, shares the same location with the magnetic North Pole. In this map, we can see how the magnetic North Pole has been shifting over the past century. There have been many moments in Earth's geological history when it has eventually moved towards the South Pole. The rocks that solidified during the periods of reverse polarity become magnetized with this reversed polarity, while the rocks forming today have a quote-unquote normal polarity. Evidence of these magnetic reversals were found in lavas and sediments all over the world. Researchers measured the magnetic polarity in numerous lava flows of different ages and used that data to determine the dates of magnetic field changes. This is how the magnetic reversals of the last million years have been accurately established, as shown in this graph. The periods of normal polarity are depicted in black, while the periods of reversed polarity are depicted in white. So in 1963, Fred Vine and D.H. Matthews connected these polarity changes with Hess's theory of seafloor spreading. They suggested that, when magma solidifies along the oceanic ridges, its magnetism aligns with the existing magnetic field polarity of that time. Over the past 700,000 years, oceanic crust with normal magnetism has been created along these global ridges. However, the oceanic crust formed about 1.5 to 2.2 million years ago shows reversed polarity. This discovery further supported Hess's theory of seafloor spreading. In 1968, the concepts of continental drift and seafloor spreading were eventually combined into a more comprehensive theory we now call plate tectonics. This theory explains how the Earth's outer layer, the lithosphere, moves and changes through processes such as subduction and seafloor spreading. These processes produce most of the geological features of the Earth, including continents and ocean basins. Understanding how this geological system works is crucial to understanding the formation of Earth's topography. So, let's start with the basics. Plate tectonics postulates that the lithosphere is composed of different independent sections called tectonic plates, which sort of float on top of the molten rock in the mantle. It all starts with the cause of these plate motions. As Holmes pointed out, it's believed that large convection currents exist in the mantle of the Earth, which involve the ascension of hot and less dense rock. It continues with the subsequent sinking of cold and dense material back into the mantle. The exact origin of these currents is not entirely clear, but their existence is quite evident. In this process, the hot materials drag the lithosphere in two opposite directions, like a conveyor belt. Once the material cools down, it sinks back into the lower mantle, where it heats up again. Additionally, the weight of the tectonic plates themselves contribute to this process as they sink, pulling down themselves, which continues to open up these oceanic ridges in the middle of the ocean. This cycle generates different types of boundaries, also known as faults, between the plates. There are three main types of boundaries depending on the type of movement that they experience. First, we have divergent boundaries, which are boundaries where the plates move away from each other, leading to the upwelling of material from the mantle. These type of boundaries are characterized by intense volcanic activity, because it's here where the new oceanic crust is actually formed. There's also seismic activity occurring at shallow depths here. These earthquakes are caused by tremors associated with the movement of the magma. A well-known example of this kind of boundary is the Mid-Atlantic Ridge. Next, convergent boundaries occur where the plates collide, often resulting in the subduction or sinking of the oceanic lithosphere back into the mantle. These regions are characterized by extremely high seismic activity, because as the plates grind against each other during this subduction, they generate earthquakes. Additionally, as subducted plates melt and fracture deeper down, new tremors are produced. Therefore, earthquakes can originate at both shallow and deep depths. There's usually some volcanic activity found at these boundaries as well. When carbon-rich rocks of the subducted plate begin to melt, large amount of lighter minerals rise back to the surface, piercing through the crust and emerging as volcanoes. Furthermore, in these types of boundaries, long mountain chains often form. As we can see in this simulation, the upper layers of sediments grind against and collide with each other, folding and producing new mountain systems. This is what happens in the Peru-Chile Trench. The oceanic plate subducts beneath the South American continental plate, and the folding of the sediments and stones has created the extensive Andes mountain range. This mountain range is home to a large number of volcanoes as well. And finally, we have transform boundaries, where the plates move laterally without creating or destroying any lithosphere. In this type of boundary, earthquakes occur at shallow depths as a result of the plates grinding against each other. If the plates move in opposite directions, like in the San Andreas Fault found along the coast of the United States, the friction between them generates a significant number of earthquakes. However, if the plates move in the same direction, such as between the African and Eurasian plates, the number of earthquakes is much, much lower. These three types of plate boundaries are the basis of the theory of plate tectonics. With this model, plate tectonics satisfactorily explains the global distribution of earthquakes. On this map, you can see the areas with the highest number of earthquakes worldwide. In this other graph, you can see the earthquakes recorded in the last 100 years. However, don't panic by the increasing number of earthquakes in recent decades. The higher number is simply due to the fact that today we have more seismographs, and they're so much more sensitive than those available 100 years ago that we detect even the smallest earthquakes, something that before wasn't even possible. Experiments have shown that a tectonic plate subducting in a subduction zone can heat up very slowly and still fracture at depths of up to 300 kilometers deep. This would explain earthquakes with epicenters located at great depths below the surface. However, the mechanisms responsible for these events, called deep focus earthquakes, which are earthquakes that occur at depths of 300 to 690 kilometers, are still not very well understood. One hypothesis suggests that during subduction, increasing pressure can change the crystal structure of certain minerals, such as olivine. This transformation could cause high-pressure failures, generating the earthquakes. The absence of deep focus earthquakes at divergent and transform plate boundaries further supports the theory of plate tectonics. By mapping the seafloor of the Pacific Ocean, a series of volcanic seamounts were discovered, extending from the Hawaiian Islands to Midway Island and continuing northwards towards the Mariana Trench. The dating of this chain showed that the age of the volcanoes increased as they moved away from the Hawaiian archipelago. Hawaii Island is the most recent volcano in the chain, having risen from the ocean floor less than 1 million years ago. On the other hand, Midway Island is 27 million years old, and the Suico Seamount near the Mariana Trench is 65 million years old. A similar situation can be observed in the Canary Islands in Spain. The oldest islands are located in the east, while the youngest are located in the west. These isolated volcanic systems in the middle of the plates, far away from both convergent and divergent plate boundaries, needed an explanation beyond the general plate tectonics theory. Volcanic systems like these, with a linear distribution along the crust, are explained thanks to what we call hotspots. A hotspot is formed when there's an upward flow of material from the mantle, often called a mantle plume. This stream of molten and extremely hot rocks can pierce straight through the thinner oceanic lithosphere and creates a volcanic area known as a hotspot. Since the plume remains in the same location while the tectonic plate keeps moving above it, new volcanoes are formed while the older ones are left behind. After millions of years, the older volcanoes erode away due to the ocean and their size diminishes. As the Pacific plate moved over this hotspot, successive volcano structures were likely formed. The age of each volcano indicates the time when it was situated above the relatively stationary mantle plume. In Hawaii, geological evidence has confirmed that the island of Hawaii is the youngest and also the most volcanically active. On the other hand, the island of Kauai is the oldest of the group and is more eroded. As we move westward, the islands are older, and many of them have been eroded to the point of disappearing beneath the waters entirely. this same concept applies to the Canary Islands. The Western Islands are younger, taller, and less eroded, while the Eastern Islands are older and flatter, and erosion has leveled their relief. After this, there was only one more discovery to explain. Wegener had proved the existence of a supercontinent called Pangaea. But recent geological studies had shown that before Pangaea, there had been several other supercontinents, such as Walbora, Columbia, or Rodinia. Thus, in Earth's 4.5 billion years of age, there was not only a separation movement, but a repeating pattern, a cycle of supercontinent formation and fragmentation. So it was then in 1968 that Tuzo Wilson proposed what would later become known as the Wilson cycle. Wilson theorized that every 400 to 500 million years or so, a supercontinental cycle would occur, bringing almost all continents together into a singular giant continent. The cycle starts with a single supercontinent that, due to its excessive size, fractures when convection current is located underneath it, causing it to fragment into little pieces. As the fragmentation occurs, new oceanic crust is formed in between. This mid-oceanic ridge continues creating new oceanic floor, and the continental sections drift apart further and further. At a certain point, the oceanic floor becomes so wide that its edges begin to cool, so at least one part sinks. A destructive boundary of sorts forms there between the oceanic and continental crust. The oceanic crust starts subducting, gradually reducing the size of the ocean. The destruction of oceanic crust causes it to shrink more and more, until the continental masses eventually come together again, forming a single large continent. And so the cycle continues. This is, of course, a very simplified version of what happens on a sphere with different continental masses and ridges and trenches with numerous plates that can push against each other. For example, nowadays, the Atlantic Ocean is growing, which leads to plate collision on opposite sides of the world. This creates a destructive boundary in the Pacific Ocean where oceanic crust is subducting it back again into the mantle. In 1977, 20 years after its original inception, Mary Tharp published a final, detailed mapping of the entire ocean floor of our planet. For the first time, we had a comprehensive view of the most remote areas of our planet, allowing us to locate all of the mid-ocean ridges, faults, and trenches that led to the discovery and identification of major tectonic plates. Plate tectonics finally came together as the theory that explained the lithosphere. So at this point, we should ask, is the Earth a special planet? Is the internal structure of the Earth important for life? To answer these questions, let's take a look at the solar system. All the rocky planets and the larger moons have a similar structure to Earth. For example, our moon has a rigid and cold crust, a partially molten mantle, and a completely molten outer core with a solid inner core. Mars also has its crust, mantle, outer core, and inner core. However, despite these similarities, there are subtle differences because in space, unlike what some people say, size does matter. We need to understand that since their formation is giant molten spheres of rock, planets have been gradually cooling down from the outside to the inside. In theory, there will come a day, billions and billions of years from now, when the Earth's crust will become increasingly larger and reach deeper into the Earth. The molten mantle will become smaller, and the outer core will also become smaller and even less fluid. Eventually, everything will solidify into a giant, rocky sphere. The interior of the Earth will be cold, and plate tectonics will stop forever. Now, back to size mattering. Smaller bodies cool down faster than the large ones. So, over the past 4.5 billion years, small celestial bodies like Mars or the Moon have cooled down faster than Earth. There is evidence that shows that both bodies had tectonic activity similar to Earth, but as they cooled down, There came a point where the crust becomes so thick that the mantle's convection currents lack sufficient strength to move the tectonic plates again. Okay, that's all fine and dandy, but maybe you're thinking, plate tectonics, who needs them? We could survive just fine without plate tectonics. What would be the problem if continents remained in the same position? You think I want my continent just ramming into another continent? That doesn't sound very convenient. Well, to answer those questions, there are two significant issues, and both are very problematic for us. The first problem is that without plate tectonics, new landforms could not be created. There would be no new mountains or any kind of uplift. So, what would happen after hundreds of millions of years if no new elevations were created? The planet would become increasingly flat due to erosion wearing away at these landforms. This might not be problematic in a place like Mars, where the presence or absence of mountains doesn't have a significant impact. However, on Earth, a planet in which the seas and the atmosphere erode the landforms, terrestrial animals would face a dramatic problem if the planet became a perfect sphere. Its entire surface would be covered in water. Terrestrial life would disappear. Only marine life would be possible. Maybe you think, okay, that's fine, I'll just evolve into a fish or a dolphin and be happy living in the ocean. But don't forget, there is a second major problem that would affect even sea life, eventually leading to its extinction. The key lies in the outer core. This layer of the Earth, highly viscous and in constant motion around the inner core, is responsible for creating Earth's magnetic field. This magnetic field, although invisible to our eyes, is essential for the existence of life on Earth. Why? Because the magnetic field protects us from solar wind, a strong stream of charged particles emitted by the sun. The magnetic field creates kind of a bubble around the Earth, acting as a shield and repelling the solar wind. Solar wind is extremely dangerous because it could strip away our entire atmosphere in just a few thousand years. In a world without an atmosphere, without gases, all of the harmful radiation from the sun would reach the surface. There would be no gases to breathe, and as soon as the water evaporates and turns into gas, it too would be expelled into space, thus breaking the water cycle. This would gradually cause the water on our planet to disappear, resulting in the loss of seas, and the most important ingredient of life itself. To get a sense of what this would look like, let's take a look at Mars, because something similar happened there. During its first billion years, Mars' interior was hot enough so that the planet could have plate tectonics, and the outer core generated a magnetic field that protected the Martian atmosphere. This allowed Mars to have oceans, a dense atmosphere, and perhaps the potential to support life during those billion years. However, as the inner layers began to cool and the outer core lost its fluidity, the magnetic field weakened. Solar wind began to blow away the atmosphere. And today, Mars is a planet with a very, very thin atmosphere, only about 1% of Earth's atmosphere. It also receives a huge amount of harmful radiation from the sun. It is a sterile and cold desert, a reminder of what Earth could be like if its interior was cold. Now that we've reached this point, we can see just how fragile and marvelous our planet is. It's an incredibly complex planet, having similarities to other celestial bodies in the solar system, but also with subtle differences that create a delicate balance that allows life to exist. Without water or an atmosphere, there would be no life. Without plate tectonics, there would be no life outside of the ocean. And without a magnetic field, there would be neither atmosphere nor water. Our planet would be a flat sphere ravaged by solar radiation and completely void of life. So thank you, plate tectonics, and thank you, magnetic field, for saving our lives. If you want to learn more, I recommend watching some of the following videos. And if you enjoyed them, leave a comment, give them a thumbs up, and subscribe to the channel. We've gone through a lot of hard work to make these videos, so doing that would mean a lot. Thank you so much for watching, and I'll see you next time.